Hello, everyone. So yeah, my name is Margarita, and I'm going to present to you a path planner that works in full 3D. That is an implementation of algorithm coming to us from more the video game side. So just want to point out that this was done in the context of the Marine US doctoral program, and thanks to Marie Curie that was funding this. Right, so this was done in Sevilla, here in Spain, in CATEC, which is a center that specializes for aerospace technology, and also with the supervision of the University of Sevilla. So why did I decide to do another planner, right? We already have plenty of those. So planners should be picked according to whichever use case they are working with. So I'm gonna show you which use case this was thought for, and hopefully this will work for you. The idea here was to use a planner that would work actually in a very large environment. Think like offshore oil rig, and also mostly focused on offshore scenarios or whichever spaces that don't have much vegetation. Vegetation here because the density of obstacles is completely different. Here you can see that the free space is grouped together in large amounts where that would not happen like in a forest. Then this algorithm also has another nice characteristic, which is it is deterministic. So for one set of inputs, you will always have the same output, which you cannot have in the stochastic ones. And it comes in handy if you're dealing with industry and you need to make certification or give some guarantees of what you are able to accomplish. So also this was done to work online and on board UAVs. So a little show of hands, who works with UAVs in the room? 1%, good, okay. A couple more in the back, cool. So the people that work with UAVs knows that one large constraint is that you have to choose carefully which processor you use. You cannot just get the best processing power on top and just slap it on. Of course, many other environments have this constraint, but because of the weight, this is really a big issue for UAVs. And also this is a planner that works fully in 3D. So just to give you an idea of how this would look like, I have a video. All right, so here you can see the planner working in the context of helping to achieve autonomous exploration. We can see here the path that has been developed by the planner in the arrows in yellow. And then you can see that it's an octomap, and the little dots are the nodes that have been evaluated in order to check if they want to be part of the plan or not. So more detail on that later. This is just for you to have a mental picture of what I'm talking about. So coming to the most important part is how to use it, right? This is actually, I think, pretty straightforward. You have here the repo where you can download the code from, and it's basically just a question of including the node in your launch file. So this was done for ROS1, not ROS2 yet. The node just works expecting to receive a message as an input, which basically has what you would expect, like your start point, your goal, also what is the maximum amount of seconds that you're able to wait for an answer, and the safety margin. So as we all know, robots are not just geometrical points, they have volume, and you probably have some constraints on how close can an obstacle get, or you might have like some localization error, or you're working outside and you have to deal with wind gusts. So here in the safety margin, you can just tell the planner how close the obstacle can get to the center of your robot. And then as an output topic, it just spits out a message that tells you whether if it was successful or not. and how many waypoints does the path have, and the ordered path. So one requirement is that your world is represented in an octomap structure. So building on the previous speaker, you already have a good idea of what a multi-resolution grid is. So I'm not going to go too much into that. I think, how many people have worked with octomap? So I have an idea. Oh, many more. Okay, so you know that this is light and has really interesting distinction of free, occupied, and unknown. And enables you to do obstacle avoidance, which is some of its strength. But for this particular implementation, it was also a source of challenge because it is so light, it was hard to univocally identify each visited voxel and to find out the neighborhood of each voxel, but these were all challenges that we were able to overcome. Then, just to give you some small details about what are the key characteristics of this algorithm, one really cool aspect is that it gives a really smooth path as compared to other graphs, other planners that work over graphs. So here you can see that the path does not hop between each node that has been evaluated. You can see that there are many, but actually the path goes from the start to an intermediate goal, and it's not like this crooked 90-degree angle between each segment. It actually has, you can have any angle between segments. So you can, depending on your objective, you can skip the post-processing smoothing, gaining some processing time. And lazy, because it does the minimum amount of obstacle checks it possibly can, and which comes really in handy because it's one of the bottlenecks. And this is just to give you an idea that, yes, it has worked in simulation, but also the jump from simulation to real world has already been accomplished. In a pending publication, I talk more about this, but just so you have an idea, yes, there were some things that had to be optimized from one to the other, but finally it worked. Using upward and on ROSCon, this was done. Just some references if you need for the algorithm, octomap, and the paper that talks more in depth about this. Do we have questions?
I'll kick us off. I was curious if you are the gazebo model or simulation that you showed in the repo that you listed, are there also simulation resources available to emulate that sort of result?
Yeah, so there is the data sets that I recovered from the laser, so you can easily just skip the whole octomap part if you have trouble in gathering some data from real life. You can use the data that is available there.
Great. Any other questions from the audience or the live stream? All right, then please help me thank the speaker once again.